Welcome back as we continue with the information handling procedures. The machine is now ready to begin the sorting operation, whilst the PLC systematically scans each input. Whenever a long block reaches the sensors, the controller handles the situation like this. The block activates both limit switches, sending an on voltage signal to inputs X2 and X3. On its next scan, the processor checks the status of each input address location and updates the input register with the latest information from these two external input devices. The on voltage signal from upper limit switch X2 means that power will flow to output coil Y2. The processor records that power has reached output coil Y2, and at the end of the scan, output address Y2 is given an on signal activating the solenoid valve. At the same time, down on rung 5, when the processor solves the logic, it will not pass power to the counter even though the examine on contacts of the lower limit switch X3 are passing power, since normally closed contacts Y2 are now in their active state, which means that they are open, thereby interrupting the flow of power to the counter. Now, you may question why we have entered a set of contacts called Y2, which belong to an output coil Y2. But remember that even though Y2 is specified as an output coil, it is an internal relay just like all the other internal logic devices, and we can use its normally open or normally closed contacts as and when we need them to pass power to other control circuits. To continue, let's see what the processor does when a short block is sensed. The short block passes under the upper limit switch and only activates the lower limit switch X3. Power passes across the rung to counter CT1 and the count advances by 1. Like any logic element, the counter symbol tells the processor to perform some very definite operations which will involve at least two registers, one to store the count and the other to compare the count with the constant 10 that we have programmed into the counter, since we want to count only 10 short blocks. In our relay-controlled system, we entered the number 10 on the thumb wheel switch, and through an electromechanical process, each count was recorded on our electrically operated counter. Under PLC control, however, we usually enter the required count directly into the user program, because the counter exists only as a logic device somewhere in the PLC's logic circuits. Most programs will show the contents of registers, but in this example we can view the actual count as it is displayed for us in the counter box. Another point to notice is the counter's reset line, which is activated by timer contacts T1. In their inactive state, the contacts are open and the counter's reset line is unaffected. But when the end of cycle timer times out, signaling the end of the sorting operation, these contacts close, resetting the counter to 0. Let's move on to rung 6. Here we find the instruction which tells the processor to make the comparison between the two registers, and when they agree or tally, to send a signal to output register Y3. When bit Y3 in the output register is set after 10 short blocks have been counted, the processor will, on its next scan, energize output coil Y3 to which the end of cycle buzzer is wired, and the buzzer will sound. You will notice that we have included a retain circuit across the counter's compare contacts to ensure that output coil Y3 remains on. This will become clear when we explain the operation of timer T1. Now let's go to rung 7 and examine the operation of timer T1. Timer functions are very similar to those of counters. The processor usually compares a preset value in one register location with the actual elapsed time being recorded in another register. And when the two values agree, the timer's contacts change from their inactive to their active state. In our example, we have loaded the timer with a constant K30, which means that the delay on time of T1 is exactly 3 seconds. So timer T1 remains inactive until the normally open contacts of Y3 change to their active state, which occurs after 10 short blocks have been counted. Once they close, rung 7 is true and power passes to the timer. It begins its timing cycle as though it was a digital clock, and when exactly 3 seconds have elapsed, its contacts change state, switching the circuits on rungs 1 and 6. Let's see what happens at rung 1. When the power flow is interrupted, the retained circuit opens. Internal relay C0 de-energizes. The conveyor motor stops, the run lamp turns off, and the stop lamp turns on. At the same time, on rung 6, the power flow to Y3 is interrupted and the buzzer stops sounding precisely 3 seconds after it was switched on. One last point to mention before closing our discussions is the circuit contained on rung 8. Notice that the last instruction in the user program is always the end statement or end coil, since the processor must know where the program ends. When the processor sees the end coil, it knows it must return to rung 1 to begin another scan cycle. This brings us to the end of Module 4, which concludes this basic series on the fundamentals of PLC control. We invite you to join us again in future programs where you can learn more on the subject of PLC managed systems.